The end of classical computer science is coming, and most of us are dinosaurs waiting for the meteor to hit. That right there is the subtitle for a paper I'm unpacking titled The End of Programming by Matt Welsh in today's episode of the CSK8 podcast. You can find a direct link to this paper at jaredoleary.com or by clicking the link in the app that you're listening to this on. This paper is only 2 pages long, so this is going to be a relatively short episode. If you don't know, my name is Jared O'Leary. I've worked with every grade, kindergarten through doctoral student in a variety of contexts like music education and computer science education. In these solo episodes, I like to talk about how scholarship relates to K-12 computer science education. In a recent interview that I did with Josh Sheldon, which is titled Empathetic Listening in Computer Science with Josh Sheldon, that's from episode 173, Josh and I talked about how AI could potentially change the field of education, and especially computer science education. Today's very short article is going to talk about this. Here's a quote from page 34, quote, "One thing that has not really changed is that CS is taught as a discipline with data structures, algorithms, and programming at its core. I'm going to be amazed if in 30 years or even 10 years, we are still approaching CS in this way. Indeed, I think CS as a field is in for a pretty major upheaval few of us are really prepared for. Programming will be obsolete," end quote. So the author goes on to discuss how they think that rather than having to write programs, you're going to train AI to write programs for you. And in the show notes, I linked to a couple of videos. One of them is like a 3-minute video, and the other is like an hour-long lecture that kind of unpacks some of these ideas more. So make sure you check out the show notes at jaredoleary.com. In those videos, the author talks about how it is very expensive to have a lot of programmers on your staff. What they're theorizing is that sometime down the road, who knows when, maybe a year from now, maybe 20 years from now, we might have one person who is going to collaborate with an AI and do the combined work of what might have taken several programmers. So if that is the case, then what does that mean for computer science education? So here's a quote from page 35, quote, "I am talking about replacing the entire concept of writing programs with training models. In the future, CS students are not going to need to learn such mundane skills as how to add a node to a binary tree or code in C++. That kind of education will be antiquated, like teaching engineering students how to use a slide rule. The engineers of the future will, in a few keystrokes, fire up an instance of a 4 quintillion parameter model that already encodes the full extent of human knowledge, and then some, ready to be given any task required of the machine," end quote. A little bit further down on the same page, quote, "In this new computer science, if we even call it computer science at all, the machines will be so powerful and already know how to do so many things that the field will look like less of an engineering endeavor and more of an educational one. That is, how to best educate the machine, not unlike the science of how to best educate children in school," end quote. And so in this paper, and again, in the 2 videos that I link in the show notes at jaredoleary.com, the author just basically talks about how the tech field continues to evolve, in computer science in particular, at a very rapid pace and in ways that we can't necessarily predict. And the author mentions in one of the videos, it's not so much a question of whether it will happen, but really when and to what extent. So if we are actually headed in this direction where maybe we don't need to know how to program, then what does that mean for computer science educators? First thing I'll say is I highly recommend actually taking a look at the comment section in the article and in the 2 videos that I link in the show notes. Some people agree, some people disagree, and some people say that we are already doing this. So for example, here's a quote from Tobias in one of the sections. So this is actually from a comment on the article itself. Quote, "I agree that AI models could very well displace humans as authors of simple and complex software components. However, I would argue that already today, writing the actual code is only a small part of my daily work as a software engineer. Much of it is indeed spent discussing and also finding the correct requirements or stories, devising the architecture, writing documentation, and generally thinking about how to keep the code base maintainable. Thus, I think that the bulk of the intellectual work of getting the machine to do what one wants will be about coming up with the right examples, the right training data, and the right ways to evaluate the training process. Is probably very true, but I would say that it is already a large part of what I do as a software engineer, although maybe in a different form," end quote. So again, that's just one of many different comments that are already on the videos and on the article itself. But this really kind of poses some questions that I think we as a field should discuss. So the first question that I have is, how will this impact CS education at large? So for example, would we need CS standards, graduation requirements, degree programs, etc.? Or would they just simply change to be modified to new understandings of computer science or new ways of engaging with computer science? Will things like standards and degrees and whatnot need to evolve at a faster rate than originally anticipated or than they currently do? For example, some states will revise their standards every 10 or so years, but will it need to be faster for computer science education? Or if you listen to the episodes from the past 2 weeks, do we really even need standards? If you haven't listened to those yet, that's episode 175, which is titled The Centrality of Curriculum and the Function of Standards, the Curriculum curriculum is a mind-altering device, and episode 174, which is educational aims, objectives, and other aspirations. But if we look even broader, what about CS discourse and how many open jobs there are? That has been one of the primary arguments that people have talked about. Well, why do we even need computer science education in our schools? Or why do we need to make it a mandate? And the biggest selling feature that people constantly cite is, look how many jobs are open in your state right now. And politicians look at that and go, wow, we could help out businesses. This would be wonderful. Let's teach computer science to kindergartners because that'll solve our problems. And while that has been a very good advocacy tool in terms of getting the message out there and selling it to people who might not understand education very well, i.e. politicians, if this actually comes true, let's say in the next 5 or 10 years, and we have one person maybe doing the job of 5, are we really going to need so many computer scientists out there? Maybe. I don't know. We might not, but odds are it's going to look very different than it does today in terms of what computer scientists do and what they need to study in order to prepare to become a computer scientist. But if you haven't listened to it yet, I highly recommend listening to episode 21, which is the CS Vision Framework and Equity-Centered Computing Education with Rafi Santo and Sarah Vogel, as well as episode 20, which is CS for What? Diverse Visions of Computer Science Education and Practice. Both of these episodes unpack, well, what kind of visions might we have for computer science education? And how might that inform what we think and do with computer science in the schools that we work with? Maybe instead of focusing on corporate needs, maybe we could instead focus on self-expression, or civic engagement, or digital literacies, or many other things that are discussed in those episodes. So I highly recommend listening to those. I know that was well over 150 episodes ago, but they're still good episodes that are relevant today. Now, if you're listening to this and you're like, yeah, okay, so we might change our discourse and we might need to change our standards more frequently, but there's still a place for computer science education in our schools, right? I've heard some people argue, like Josh Sheldon in a previous interview, which was a great interview, by the way. Thank you, Josh. Some people would argue, hey, we should focus on computational thinking. This will help us be able to think as a computer scientist to be able to communicate with AI, who will then generate programs or code for us. Now, that idea is something that really struck me in my interview with Josh. And I really was kind of grappling with that and have been ever since that conversation. So I want to just share some of my in-process thoughts on this. I've been very critical of computational thinking. I think we should instead focus on computational literacies, which is discussed in episode 111 titled A Reevaluation of Computational Thinking in K-12 Education, moving toward computational literacies. A problem that I see with the argument for computational thinking is that it is a vague collection of ideas and tools that are not unique to computing or problem solving. So if instead of writing lines of code, we are going to run some models and give it to some AI and then ask the AI to write code based off those models, and then test their output. Aren't there other forms of thinking that would also assist with this, that are less vague? So for example, might we use the scientific method? So we would come up with a hypothesis and run some kind of an experiment to determine whether or not the generated code works as intended. Would we then need to understand how to reverse engineer where the problem is in order to fix it, if it doesn't work as intended? Or would we just keep saying, hey, computer, try it again? If we could identify a very specific problem with it, would we ask the AI to fix it, or would we have to fix it? What about a different approach? What about the Socratic method? So a lot of these generative AI platforms are more conversational. So might we engage in dialogue with AI to better understand an idea or to test a hypothesis? Depending on how the AI is designed, perhaps one of these methods or approaches or frameworks, etc., might be more beneficial to think of than just saying, hey, I'm going to engage in deep composition or abstraction and problem solving, and then that's going to help me communicate with AI. Those are just two very quick examples that came to mind in terms of how we might be able to think about this. I'm sure there are even more that are much better at thinking through this. Or perhaps we need to create one, rather than just trying to crowbar some different tools into a new way of thinking. But to argue with myself, I wouldn't even necessarily call those tools as much as they are just kind of broader concepts or labels. So to draw on teaching as a metaphor, because it was being used to talk about how we're going to train AI by teaching it. Okay, so saying that computational thinking involves pattern recognition or decomposition, abstraction, etc., is like saying teaching involves delivery of content and classroom management and assessment, etc. I agree, it does involve those 3 things and more, but the level of variance that one can take when we actually get granular with each of those topics is so immense that you could spend literally years and multiple degrees just studying one of those things and still not run out of different aspects that you could explore in each of those areas. So for me, I just think it's a little absurd that we kind of focus on those broader labels, like saying, well, as a teacher, you engage in classroom management, rather than actually talking about, okay, well, how do you manage classrooms, and in what context and in what ways? And when would you do it one way and not another way? I think the same thing can apply for, okay, well, how are you going to recognize patterns? Or how are you going to decompose? When are you going to choose one decomposition approach versus another one? So I'm still not convinced that computational thinking is actually a thing as much as it is just a collection of like broader terms that are kind of like being thrown together and saying, this right here, this is what computer scientists do to be able to think, without actually labeling or defining, okay, well, what do each of those look like? What are the variances within decomposition? So maybe computational thinking is the thing that we will need to be able to work with generative AI to create a program in the future. Maybe. I doubt it, though. First, I think we need to figure out what the definition of computational thinking is. And then I think we need to figure out, okay, well, what are each of the subsections or components of computational thinking? If we all universally agree that decomposition is an aspect of computational thinking, great. Now let's talk about the different approaches for decomposition within that. Then we can actually get to something useful. And as always, when I go on these little computational thinking rants, if you disagree with me, I'm happy to have you on the podcast. I'd love to talk to you about it, to like genuinely try and understand where you're coming from and why you think computational thinking is the answer. Maybe I'm just reading the wrong materials, but I have not really seen yet a convincing argument for why we should do computational thinking. As I asked in a summit many years ago, this was like in 2017 or something like this, and it was a summit on computational thinking. I had a question of when is it not computational thinking? Because everything that I was seeing is like, oh, well, when you tie your shoes, when you're like walking to the store, all of that is computational thinking. And it just seems like we're kind of crowbarring it into anything and everything we can to the point where it's gotten so broad that it's like meaningless. And as a field, we have still yet to define, well, exactly what does it mean? What does it look like? So I'll end that rant there. But there are more episodes that talk about computational thinking, and I include links to those in the show notes at jaredoleary.com. But now I want to kind of go back to the paper itself, and I want to problematize one of the key ideas. So if the shift is from doing the programming to teaching a machine what to program, I would argue that we still need to understand how to program to do that. Why? Well, I mean, maybe we need to verify if it will work as intended with an existing program, or we need to be able to modify it. If we are going to create apps that do very specific things for specific people, or even for a broad range of people, we need to be able to customize it for those different audiences or users, etc. So yeah, you might not be doing the majority of the programming, which sounds great, but you're still going to adjust some things. I doubt people are just going to go with the default answer that is given to you. Maybe, again, that will be done through some kind of a dialogue with the AI to be able to customize things, or you might go into the code and change the parameters around a bit. But perhaps a better argument is that teachers aren't just spoon-feeding examples to students that they don't understand. If they were, how would they be able to assess whether or not a student actually understands the content? So if you're engaging in some kind of a large project where you are, I don't know, like coding a video game or something, and you're working on the physics engine for it, you might say, hey, AI, I'd like you to be able to code making it so that I can throw something in the game. We've already got code for movement, we've already got code for jumping, but I want to make it so that when I throw something, it's not just gravity that affects it, but it also can hit an object and bounce off of it. So if we have a wall and you throw a rock at the wall, it's going to hit the wall and then continue to fall, but bounce backward. If I told the AI that, hey, I'd like to be able to add in a physics component for something being thrown, it might spit out code that says, hey, this object is going to move at 9.8 meters per second, and then some kind of a code that'll make it so it'll detect and bounce off of a wall or some kind of an object while it continues to move, etc. But you're going to need to be able to figure out whether or not it's actually going to work within your platform. For example, how is it going to interact with other sprites? Like instead of a wall, what if you throw it and it hits an enemy in the game? How is the enemy going to respond to it? Is it going to bounce off of them? Will it do damage to them? What about if you throw it at a friendly character? Are they going to get upset at you? Is it going to change your relationship option with them? Are they going to pick it up and throw it back at you? All of these little conditions need to be programmed into what it is that you are creating. So if you're just asking AI for the general physics engine or the algorithm that's going to be used to code the object that's being thrown, great. But now you have to make it work. It's kind of like when you go into Stack Overflow and you're trying to find like a solution to something. You might find a general idea, but you're going to have to adjust the parameters. You're going to have to make it fit like within what you are actually writing. If you just copy and paste the answer and put it into your code, odds are it's not going to work. And my guess is for quite some time, it's going to be the same thing with generative AI until it gets to the point where AI can develop the entire platform, the entire project start to finish and analyze all of the code and make the adjustments all at once. You're still going to need to know how to program, or at least evaluate a program in order to make it work, in my opinion. Eventually, I'm sure we'll get to a point where it's just as good as the author describes, and all we have to do is come up with ideas. Until then, we're going to need to know something. But even at that point, that's still just one of the components of like the standards for computer science education, like CSTAs. So algorithms and programming, great. I think we should focus on them, but there's also computing systems, there's networks and the internet, there's data and analysis, there's impacts of computing, etc. There's more to computer science than just coding, which a lot of people have been saying for a long time. But just because I can use a graphing calculator to figure out a math problem instead of using a pencil and paper, I'm still engaging with math. So in the end, you might not be doing the rote, mundane aspects of programming, writing out lines of code, etc. I would still argue that you need to understand programming. It just might be in ways that are different than we are currently doing or currently teaching. And that's okay. That's to be expected. I would hope that anything related to technology, any of the concepts, practices, understanding, etc., if you were to take a snapshot of education in K-12 right now, or even in higher education, what is going to be taught and how it is taught, I imagine is going to look very different 10, 20 years from now. And if not, then we got a problem. But these are just my opinions in response to the author's article. I highly recommend taking a look at the article and listening to the videos that I link to in the show notes at jaredoleary.com, and I highly encourage engaging in a conversation with the field. You can share this episode with the article as well as the videos with other colleagues and start a conversation. Do you agree? Do you disagree? How do you think this impacts what you do or what you might be doing 5 or 10 years from now as an educator? I think it's a really interesting thing to explore, and I look forward to seeing how this all turns out. Thank you so much for listening to this podcast. If you enjoyed it, consider sharing with someone else. Stay tuned next week for another episode. Until then, I hope you're all staying safe and are having a wonderful week.